Breaking, Webb discovers the farthest star known to humanity. In an astonishing leap forward for astrophysics, the James Webb Space Telescope, JWST, has uncovered the most distant star ever observed. Dubbed Enderle, this celestial object sits approximately 28 billion light-years away from Earth, its light having traveled across the vast expanse of space for more than 13 billion years before reaching our telescopes. This discovery allows us to look back at a time when the universe was less than 1 billion years old, offering a rare glimpse into its formative years. The revelation of this star, dating back to the early cosmic dawn, not only marks a groundbreaking milestone in our quest to understand the universe, but also opens new doors to studying the first generations of stars and galaxies that shaped everything we know today. This article will explore the technological marvel that is the James Webb Space Telescope, how Enderle was discovered, why this discovery is so significant, and the profound implications it has for the future of space exploration and cosmology. The James Webb Space Telescope, a marvel of modern science. The James Webb Space Telescope is the most powerful and advanced space telescope ever constructed. Designed to surpass the capabilities of its predecessor, the Hubble Space Telescope, Webb is equipped with cutting-edge instruments that allow it to observe the universe in unprecedented detail. JWST was launched on December 25, 2021, and it orbits at the second Lagrange point, L2, approximately 1.5 million kilometers from Earth. From this position, the telescope enjoys an unobstructed view of the cosmos, far from the interference of Earth's atmosphere and sunlight. What makes JWST particularly extraordinary is its ability to observe the universe in the infrared spectrum. Unlike visible light, which can be blocked by dust and other obstacles, infrared light can pass through these barriers, allowing astronomers to see celestial objects that are otherwise hidden from view. This feature is critical for studying the early universe, as light from the most distant objects has been stretched into the infrared spectrum by the expansion of the universe, a process known as redshift. By capturing this redshifted light, JWST effectively acts as a time machine, allowing scientists to observe the universe as it was billions of years ago. JWST's primary mirror, which is 6.5 meters in diameter, is made up of 18 hexagonal segments coated with a thin layer of gold, enhancing its reflectivity in infrared wavelengths. The mirror is more than twice the size of Hubble's, giving JWST an unprecedented level of sensitivity. This allows it to detect incredibly faint objects that are billions of light-years away, such as Enderle, the newly discovered star that lies at the very edge of the observable universe. The discovery of Enderle, a cosmic miracle. In March 2022, astronomers announced the discovery of a star whose light had traveled for over 13 billion years before being detected by JWST. Named Enderle, an Old English word meaning morning star, or rising light, this star is the most distant individual star ever observed. It is located in a galaxy far beyond any previously studied star, during a period known as the Epoch of Reionization, when the first stars and galaxies began to form and illuminate the universe. The discovery of Enderle was made possible by an effect known as gravitational lensing, which occurs when a massive object, such as a galaxy cluster, bends and magnifies the light from objects behind it. This phenomenon was predicted by Albert Einstein's general theory of relativity, and has been used extensively by astronomers to observe distant objects. In Enderle's case, a massive galaxy cluster called WHL 0137-08 acted as a gravitational lens, amplifying the star's light by thousands of times and making it visible to JWST. Without the gravitational lensing provided by WHL 0137-08, detecting Enderle would have been impossible, even with the James Webb Space Telescope. The star is located in a region of space known as the sunrise arc, where the light from distant objects is magnified by the gravitational effects of the galaxy cluster. This natural magnification allowed JWST to observe Enderle as it existed just 900 million years after the Big Bang, offering a rare glimpse into the universe's early history. Prior to the discovery of Enderle, the most distant star ever observed was Icarus, detected by the Hubble Space Telescope in 2018. Icarus existed about 9.4 billion years ago, making Enderle's discovery even more remarkable, as it pushes the boundaries of what we thought was possible in terms of stellar detection. Why the discovery of Enderle matters. The discovery of Enderle is not only a record-breaking feat in terms of distance, but also a crucial step toward understanding the early universe. During the epoch of reionization, the first stars and galaxies began to form, bringing light to the universe after the dark ages that followed the Big Bang. Studying stars like Enderle provides astronomers with an invaluable opportunity to explore this period and learn more about the processes that shape the cosmos. One of the most exciting aspects of this discovery is the possibility that Enderle may belong to the first generation of stars, known as population 3 stars. These stars are thought to have been composed almost entirely of hydrogen and helium, the two elements produced in the Big Bang. Unlike later generations of stars, which contain heavier elements like carbon, oxygen, and iron, population 3 stars were incredibly massive, hot, and short-lived. They are believed to have played a crucial role in enriching the universe with the heavier elements necessary for the formation of planets and life. Although no direct evidence of population 3 stars has been found, Enderle offers a tantalizing clue. If it is indeed a population 3 star, it could provide the first concrete evidence of these primordial objects, helping scientists understand how the first stars formed and evolved in the early universe. Furthermore, studying Enderle could shed light on the process of cosmic reionization, a pivotal phase in the history of the universe when the first galaxies and stars ionized the neutral hydrogen that filled the cosmos, making the universe transparent to light. Understanding this process is essential for piecing together the timeline of cosmic evolution and learning how the universe transitioned from the dark ages to the bright, structured cosmos we see today. The science behind Webb's observations. Detecting a star as distant and faint as Enderle required the unique capabilities of the James Webb Space Telescope. The telescope's near-infrared camera, NIRCam, and mid-infrared instrument, MIRI, were essential in capturing the light from this distant star. NIRCam is designed to observe the universe in near-infrared wavelengths, which are critical for detecting redshifted light from the earliest stars and galaxies. MIRI, on the other hand, operates in the mid-infrared range and is capable of analyzing the chemical composition of these distant objects by studying the light they emit. Webb's ability to perform spectroscopy is another key tool in the study of Enderle. Spectroscopy allows astronomers to break down the light from a star into its constituent wavelengths, providing information about the star's temperature, chemical composition, and velocity. By analyzing Enderle's light spectrum, scientists can determine whether it is composed primarily of hydrogen and helium, as would be expected for a population 3 star, or whether it contains heavier elements, indicating that it is part of a later generation of stars. JWST's large mirror and advanced instruments also allow it to gather more light than any other telescope, making it possible to observe incredibly faint objects that were previously beyond our reach. This increased sensitivity is crucial for studying the early universe, where the light from distant stars and galaxies is often faint and redshifted into the infrared spectrum. In addition to its infrared capabilities, JWST's position at the second Lagrange point, L2, allows it to operate in a stable environment, free from the interference of Earth's atmosphere and sunlight. This stability is essential for making precise observations of distant objects like Enderle. The broader implications for cosmology and astrophysics. The discovery of Enderle has far-reaching implications for our understanding of the universe and its early history. By studying stars like Enderle, astronomers can gain new insights into the formation and evolution of the first stars and galaxies, as well as the processes that shaped the universe during its infancy. One of the most exciting prospects is the potential to find more stars and galaxies from the epoch of reionization. JWST's ability to observe distant objects in the infrared spectrum makes it ideally suited for exploring this period, and scientists expect that many more discoveries, like Enderle, are on the horizon. These discoveries will help fill in the gaps in our understanding of cosmic history and provide new clues about how the first stars and galaxies formed and evolved. Another important implication of Enderle's discovery is its potential to shed light on the Hubble tension, a long-standing discrepancy between different methods of measuring the expansion rate of the universe. The Hubble constant, which describes the rate at which the universe is expanding, has been measured using several different techniques, but the results have not been consistent. Observations of distant stars like Enderle could provide new data that help resolve this tension and refine our understanding of the universe's expansion history. Additionally, Enderle's discovery offers new opportunities for studying dark matter, the mysterious substance that makes up about 85% of the matter in the universe. Gravitational lensing, the phenomenon that made Enderle's discovery possible, is caused by the gravitational effects of dark matter in galaxy clusters. By studying the way dark matter distorts and magnifies the light from distant stars and galaxies, astronomers can learn more about its properties and distribution, providing new clues about the nature of this elusive substance. What comes next? The discovery of Enderle is just the beginning of what promises to be a new era of exploration in the early universe. JWST will continue to observe distant stars and galaxies, pushing the boundaries of what we know about the cosmos and uncovering new insights into the formation and evolution of the universe. One of the next steps in the study of Enderle will be to perform more detailed spectroscopy to determine its chemical composition and confirm whether it is indeed a population 3 star. If this is the case, it would represent a monumental breakthrough in our understanding of the first stars and the conditions in the early universe. In addition to studying individual stars like Enderle, JWST will also focus on finding and analyzing the earliest galaxies. These galaxies, which formed just a few 100 million years after the Big Bang, hold the key to understanding how the universe evolved from a featureless void to the complex, structured cosmos we see today. Furthermore, JWST will play a crucial role in the search for the first supermassive black holes, which are thought to have formed shortly after the first stars and galaxies. These black holes likely played a significant role in shaping the evolution of galaxies, but their origins remain a mystery. By studying the early universe, JWST could provide new clues about how these black holes formed and grew to the enormous sizes we observe today. Conclusion: the discovery of Enderle, the farthest star ever observed, marks a monumental achievement in the field of astronomy. This incredible finding not only pushes the boundaries of what we thought was possible in terms of stellar detection, but also opens new doors to exploring the early universe and understanding the processes that shape the cosmos. With the James Webb Space Telescope's unprecedented capabilities, we are entering a new era of discovery, one in which we can look back billions of years and witness the birth of stars, galaxies, and black holes. As we continue to explore the cosmos with JWST, we can expect many more groundbreaking discoveries that will reshape our understanding of the universe and our place within it.